So, as all of you know, me too, Fourier coefficients of cusp forms in general are mysterious objects. If you think of the tau function, for example, from Mandelbrot's tau function, quite a mysterious function. In particular, if these Fourier coefficients are real, their sign changes are, or the distribution of the signs are mysterious. And one wants to understand what's going on here. So, using the theory of L functions, one can comparatively easily show that if you have given a cusp form non-zero of even integral or half integral weight on a congruent subgroup of the full modular group, then the sequence of Fourier coefficients, if they are real, have infinitely many sign changes. So infinitely many n such that the coefficient a sub n is positive, and the infinitely many n such that the coefficient a sub n is negative. After that, then one may ask more specific questions, for example, about the number of sign changes in intervals, or one may ask about the first sign change, when does it occur? Once explicit bounds in terms of the weight and the level and something like that. So in my talk today, I'll firstly address this last question in the case of elliptic cusp forms and try to tell you what's known about that or what has been proved recently about that. And then in the second half of the talk, I will go over to Siegel modular forms of arbitrary genus where the situation is much, much more complicated. So just let me start with the classical case and give you introductory results. So this is elliptic modular forms. And the whole thing, in a sense, started with the following theorem, which is due to Marvin Knopp, Vlad Pripyatkin, and myself, and it appeared around 2003 in some journal. And the result says the following. So let f non-zero be a cusp form of weight k. So the k may be an integer or half integer, or more generally you can talk about multiplier system on a congruent subgroup so say gamma inside the full modular group, which is abbreviated by gamma 1. And with Fourier coefficients an real for all n, then the sequence a sub n and running over all positive integer has infinitely many sign changes. In fact, Jeff Mason around 2002 asked Marvin Knopp about this question, and Marvin passed on the question to me, and I could, together with his help, give some rather easy solution of that using Rankin-Selberg zeta functions. But then Marvin was looking, it was not elementary enough for him in a sense, so he wanted something more elementary, and then he came up with some other ideas, and altogether with Pripyatkin we wrote a paper in a very general context. So I'd like to give you idea of the proof. So it will be sufficient to assume that a of n greater or equal than 0 for all n greater or equal than 1, and to derive a contradiction, because you can always change f to minus f. And now let me denote by Lf of s, the classical L function attached to f, Hacker L function from a of n to the minus s. So this is convergent if the real part of s is large enough. And now you explored a very classical theorem of Landau on Dirichlet series with non-negative coefficients. So with Landau's theorem, This is with non-negative coefficients. And this, in the context here, says the following. So there exist exactly two alternatives. One, and the f of s converges for every complex number s, or secondly, and f of s has a singularity and in fact at the real point of its abscissa of convergence. But of course f is a cusp form, so we know by Haeckel that LFS extends to an entire function so this implies that one must hold, of course, which is a little bit absurd, of course this can't. The question is how to put that down technically. So of course if this is true, then the coefficients a of n are bounded by n to the alpha for all alpha in R. And you can also put the square here, or for all alpha in R, and this implies Rankine-Dirichlet series Rf of s defined as sum an squared over n to the s is entire. And this is a contradiction because we know by Rankine-Selberg or f of s as a pole at s equals the weight and the residue up to some universal constant is given by the Peterson scalar product, which is non-zero by our assumption f is not zero. So this is very easy. Now, to investigate the question, when does the first sign change occur? And what is wanted here is an explicit upper bound in terms of the weight and the level. And so the first thing we may look for, or the most interesting thing maybe not, is to look at eigenforms. So this case was considered by Choie and myself, and then there's a subsequent paper by Ivanec, Choie, and myself. I'd like to give that. I think it was done in 2007. So let F be a cuspidal normalized Haeckel eigenform that is a new form of weight k integral at least 2 on the Haeckel congruent subgroup gamma 0 n. So I just record the definition ABCD in SL2Z such that n divides C. So these assumptions apply, of course. Normalized means A1 is 1. So this is positive, and A of n at the nth Haeckel eigenvalue And now let me define quantity Q to be K squared times N. And sometimes it's called the analytic conductor. And we have a bound now in terms of the analytic conductor. So the result goes as follows. Then there exists n with a of n negative and n bounded by some absolute constant. We take the Q 29 over 60. So it's a little bit better than 1/2. 1/2 is a usual convexity bound. It's a little bit better. And the thing is that the proof is rather elementary. It depends what you mean by elementary. No use of convexity bounds. For L functions. And the main idea is just estimate sums like that. Actually, we can also suppose that, if you like, not so important, that n is prime to capital N. Estimate sums like that, sum n less or equal to x, and if you want the extra condition, you can put it down here, a of n, and then eventually take a smoothing function, log x over n from above and below, using the multiplicative properties of the sequence a sub n. Of a of n. So this really needs the fact that f is a Hacker eigenform. Now this result has been improved by several people in subsequent years. Improvements. Exists n with a n negative. Such that first n less than q, it's 9 over 20, and this is due to Kowalski, Yukam Lau, J. Wu, and Sound. It was done, I think, 2010. And this has been further improved by Matomeki. She can go down q to the 3 over 8. And 12. And in the case where the level is 1, this has been again improved. K to the delta. This delta, some number less than 1/2, just in case n is 1, by Gauche and Sanak. Also 2000. This is an important application for L functions, series of L functions. Okay, now the question is, what can we prove or what can we show for arbitrary cusp forms if we don't assume Hacker eigenform? And there's a result by Choie and myself a few years ago. And this goes as follows. Yongju, 2009. So suppose, just for simplicity, n is 1, or n is p prime. We have a more general result also in other cases for n, but I'm just stating that because it's relatively easy to state. So let f non-zero be some cusp form of weight k on gamma 0 n as before. And there exists positive integer n, 1, and a positive integer n2, such that n1 and n2 bounded in absolute constant, which may depend on p, so on n. And now we get k over 5 log 26 of k, and such that a n1 is negative and a n2 is positive. This was technically quite hard to prove, and in fact we are far away from actually what one would expect. What one would expect for an arbitrary cusp form is just k to the 1, maybe some log term by a prototype of result due to Siegel. But we are far away from that. So I give the idea of proof just in a few words. So use the result for new forms plus special basis of old forms. By special, I mean the basis should be appropriate in a certain way for the bad Heck operators acting. And so write f as a linear combination of the corresponding new and old forms. And then at some point we use elementary device Chebyshev inequality. And also good lower bounds for the scalar product for Hecker eigenform with itself due to Jeff, Hofstein, and Lockhart, G Hecker eigenform. This is due to Hofstein. And on the way, if you do this, you're actually losing some powers of k, so you end up with a k to the 5, essentially. Maybe possible to improve that a little bit. Okay, so this seems to be the situation in the case of elliptic modular forms. And now in the remaining time, I'd like to try to give you some idea of what one may expect or what one can prove in the case of Siegel modular forms, arbitrary number of variables. So, I like to recall some of the basic notations in this story. So we fix a positive integer g called the genus, and then we have the symplectic group gamma g, sp Z sitting inside GL2G Z, symplectic group of size 2G over Z. And there's a corresponding symmetric space. So gamma G acts on the Siegel upper half space HG, consisting of matrices of size G, complex G by G matrices, which are symmetric and which have positive definite imaginary parts. So this is an obvious generalization of the classical upper half plane if G is 1. And the action is, as you would suppose it should be. So you split up a matrix into block matrices A, B, C, D, each of size G, and apply it on Z. This is AZ plus B, CC plus D inverse, because you have to check that this really is an operation. And let me fix a weight, K, and write SK gamma G. This is the space of Siegel cusp forms of weight K and genus G. So let me give you the definition. So these are holomorphic functions f on Hg going to C that enjoy the following transformation formula. So you take f Az plus b, cz plus d inverse, and then this should be a determinant of cz to the weight k times f for all substitutions a, b, c, d, and gamma g. And you want an appropriate Fourier expansion, and the Fourier expansion in that case has the following shape. So you take some coefficients a t, e to the 2 pi I trace tz, and t is positive, FFC, where t runs over all positive definite half integral matrices of size G, where by half integral I mean that the integers, the entries are in 1/2 Z, and on the diagonal they are actually integers. So this is a finite-dimensional vector space. We can show using induction theory. It's not quite as easy as in the classical case. It has to do some work. And now one may ask for L functions and also for sign changes. And now there's this important observation, which actually gives a lot of trouble in the theory. So if U is a unimodular matrix in GLZ, then you immediately check that U transpose 0, 0, U is symplectic. And if you act with such a matrix on F, then you see that F U transpose Z, U is F of Z times determinant U to the power K. And now you go into your Fourier expansion, and then you see that A du is equal to determinant T to the power K times AT for all U in GLZ for all T positive, where this is the usual notation TU U transpose T U. So if K is even, for example, then the coefficient is invariant under the action of GLG, and this gives the trouble in defining an L function. So still one may ask for sign changes of the coefficient A of T, where T runs modular the action of GLG. And this was done a couple of years ago by one of my students, Stefan Jeskarts. Paper appeared somewhere, I forgot where. So Stefan proved the following. So 9. Suppose that F cusp form of weight K and gamma G, F not the zero function, and also suppose that K is even, A of T is real, all T positive. Then there exist infinitely many T positive modulo the action of GLZ such that A of T is positive and such A of T negative. And the proof follows more or less the same idea as in the case G equal to 1. So follow the same idea as in G equal to 1. However, you have to place the L functions by appropriate other objects. So you place the Hecke L function L of S by the Kocher-Maas series. And their annuity properties have been proved by Maas. And you also have to look at the Rankin-Seilbach zeta function in arbitrary genus, which is rather difficult, but the results are there. And we can put that all together and then use Landau's theorem and get the result. So we place L Fs by Kocher-Maas. Series. Also use properties of the Rankin-Seilbach zeta function Rf Fs. Okay, now I think I have still 10 minutes. So I'd like to report on very recent work by Shonley, Young-Ju, and myself, which was just finished a couple of months ago, and where we look at the case of an arbitrary non-zero cusp forms and on sign changes for that. So, theorem. So I do the same assumption as there. That F in SK gamma G F non-zero. Of course, here I have to suppose. Sorry, I didn't say that. Oh, I did say it. AT is an R. Okay, sorry. That's correct. K even and AT real, or T greater than 0. Then there exists T1 and T2 positive definite matrices such that the trace of T1 and also the trace of T2 is bounded by some absolute value K times Cg to the power 5 times log 26 Cg times K, and 81 is positive, and 82 is negative, and Cg is just a constant depending only on G. It's G times 2 to the G minus 1, 4 over 3 to the G times G minus 1 over 2. So it's not accidental that you have the 5 here and the 26, the same exponents as before in the one-dimensional theory. And in fact, we reduce everything to the one-dimensional theory, but it's technically pretty hard. So 6 minutes left. Try to give a very short outline of the proof. So of course it's sufficient to show axis T with trace T in the given range and a T negative, because again you can always replace F by minus F. And now you use general theory, in particular reduction theory. First step. So there exists a T naught, positive definite, such that the trace of T naught is bounded by some constant depending on G times K. This constant may be very explicit, so we can write it down very explicitly. It follows from reduction theory. So we always have this, and of course the most important thing, an A T naught non-zero. So in this range you can always find a non-zero coefficient. And now the idea is to use Fourier-Choie expansion. So you write T naught as N naught, R naught over 2, R naught over 2 transpose, M naught, where N naught positive integer, R naught is a vector, size G minus 1, and N naught positive definite, size G minus 1. And then look at the corresponding Fourier coefficient, phi M naught, tau Z, tau NH, Z and C to the G minus 1. Fourier-Choie coefficient of F of index M naught. So this is a generalized Jacobi form on the group SL to Z, now acting on Z to the G minus 1 cross Z to the G minus 1. And so this has a transformation formula with respect to SL to Z, and also with respect to pairs lambda mu in this group here, and also has a corresponding Fourier expansion. So transformation formula with respect to gamma 1 and Cg minus 1 cross G minus 1. Of course, if G is 2, you are back in the classical situation, which was considered by Ramke yesterday. And this thing also has a Fourier expansion. And of course, the Fourier expansions are some of the Fourier expansion of the original function f. This is the most important thing by definition. So phi M naught coefficient C and R and tau R1 Z1 R z minus 1 n greater or equal than 0, r in z to the g minus 1, and you have the condition on positive definite, it's m naught inverse r transpose. I think it looks like that. Okay, and now what you do, you look at the Taylor expansion of this function phi m naught around z equal to 0. So the coefficients chi nu 1 up to nu g minus 1 of tau, z1 nu 1 up to z g minus 1 nu g minus 1, and the nu's are running over non-negative. It's a cusp form, so running over non-negative integers, greater or equal than 1. So, and now there's an important step. We choose, so this is not 0, of course, by m naught. It's not the 0 function because the coefficients 80 naught comes in the full expansion of phi m naught. And now choose alpha 1, alpha g minus 1 minimal in a certain way such that chi alpha 1 alpha g minus 1 of tau is not identically 0, not the 0 function. This can be done, and then it turns out, of course you have to prove that, I think it's rather non-trivial. This implies that the function h of tau chi alpha 1 chi alpha g minus 1 of tau is an elliptic cusp form. I have 1 minute. This is an elliptic cusp form of some weight on SL to Z, and the weight can be given in terms of the weight k you're starting with, and also with respect in terms of the trace of m naught. Weight k1 bounded by k trace m naught. So in my last minute, I'm going to explain how this works in the case g is equal to 2. So then you have just one variable here, one index here, and one index there. And then you have chi naught, chi 1, chi 2, and so on. And as Ramke pointed out yesterday, chi naught is a modular form. Chi 1 is a modular form up to correction terms coming from chi naught prime. Chi 2 is a modular form up to correction terms coming from chi 1 prime, chi naught double prime. So if you choose alpha in a minimal way, then there are no lower terms. So if you choose alpha in a minimal way, then chi alpha has to be a cusp form of weight k. And then if you do it, the calculations of weight k plus alpha. But now there is a fundamental result in the book of Eichler's AG, since the Jacobi form is something like an elliptic form in the second variable. The smallest alpha, such that this is not 0, always is bounded by 2m, where m is the index. And this generalizes to the higher dimensional case after some hard work, I think. We really struggled for that for some time, but it works. And now, in the final step, you use, let me write that down, then I'll finish. Use the result of Jung-Ju and myself for h of tau, in conjunction with the fact that h of tau can also be obtained by a multi-partial derivative of this function with respect to the variables z1 up to zg minus 1, and then putting z equal to 0. And if you do that, you get up then from this definition C and R's and some powers R1, J1, R2, J2, and so on, and then you apply the result of Choie, and after some work you finish. It's not, I'm a little bit oversimplifying because you really have to, it doesn't work like that. I mean, it's not true. You have to assume that the function phi m naught is even with respect to each variable. In general, this is not true, but you can make a trick. You can just symmetrize. You take the product. So what you have to do is the product of all signs phi m naught tau epsilon z, which again is a Jacobi form of weight k times 2 to the g minus 1 and some index, and then you work with that function. And I think my time is over now.
Are there any questions or comments? Yes.
What happens if you apply the naive Rankin-Selberg method for Siegel modular forms and use the standard convexity estimates?
We haven't checked this.
Comparing that with the result you have, right?
Yes, yes. I think the theory of Jacobi forms always is a very nice bridge between Siegel modular forms and elliptic modular forms. Many examples for that. And this is another example how it works nicely. Yeah, one could try.
Try to compare.
Yeah.
Are there further comments? Otherwise, let's thanks to the speaker for interesting talk. So we will resume at 10.